Okay, so in this section we're going to discuss about two different rules, addition and multiplication for the probability. Okay, so let's say you have two events A and B, and if we would like to find out what is the probability of happening A or B, that can be found by using addition rule. Okay, and what is the probability of happening A and B together? Look at here. Find out the probability of happening A and then B. That's called multiplication rule. Okay, so we have to introduce this event called compound event, which is combining two or more simple events. A compound event is any event combining two or more simple events. So the addition rule, if you would like to find out the probability of finding A or B, then first of all we need to find out probability in a single trial, event A occurs or event B occurs or they both occur. That's the meaning of probability of A or B. To find this probability A or B, add the number of ways event A can occur and the number of ways event B can occur, but add in a such a way that every outcome is counted only once, so we cannot count it twice. Probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. We are going to see example, but before that, this is the formula we need to use. Probability of finding A or B can be calculated by using this formula, which is probability of A probability plus probability of B minus probability of A and B, where probability of A and B denotes the probability that A and B both occurs at the same time as an outcome in a trial of a procedure. That's the addition rule. Okay, before we apply this addition rule, we have to understand either our events are disjoint or or not, so which is also called mutually exclusive events. Two events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. For example, think about tossing a coin with the head and tail. In a single trial, head and tail, they cannot occur, both cannot be possible. So they are disjoint event. Event A, randomly selecting someone for a clinical trial. This is another example. Let's say in a clinical trial, there are two events. One is randomly selecting someone for a clinical trial who is male, and second one is female. So when you try to randomly select a person for a clinical trial, it has to be either that person has to be either male or female. It cannot be both. So these two events A and B are mutually exclusive, or also called disjoint events. Another example here, randomly selecting someone taking a statistic course, that is the event A, for example, and event B is randomly selecting someone who is a female. So when you try to select randomly one person, that person could be female who is taking statistics. So both of the event could happen together. That's why it's not disjoint. Okay, so the summary, here is a summary. If you would like to find out probability of happening A or B, first associate the word or with addition. So or means addition. To find the value of this probability, add the number of ways A can occur and the number of ways B can occur, but be careful to add without doubling counting. Okay, so one thing, I already discussed about this thing in previous section, but I'm going to repeat it. Probability of happening A or its complement is everything. So A and its complement, probability of happening A or its complement is equal to probability of happening A plus probability of happening its complement, and this would be equal to 1. Think about tossing a coin and getting head is A and getting tail is its complement. So what is the probability of happening head in a single toss of coin? It's a half. What is the probability of happening tail in the single toss of coin? It's again half. So probability of head or tail is half plus half, which is actually 1. Okay, because they are disjoint, they are complement. So whenever you add the probability of any event to its complement, the sums would be always 1. You can find the probability of complement event by subtracting probability of the event from 1. So these are the relation we can use for the complementary events. Let's see one example. Based on survey results from the Consumer Technology Association, the probability of randomly selecting a household in the United States and getting one with a smartphone is 0.87. 0.87 means it's 87%. If you randomly select one household, then 87% chance is that household is using smartphone. So what is the probability of a smartphone? It's 0.87. If a household is randomly selected, find the probability of getting one that does not have a smartphone. So which is complement of this having a smartphone. So which can be found by using this complementary rules, which is 1 minus having a smartphone, which is 1 minus 0.87, which is 0.13. Okay, so probability of finding household not having a smartphone can be found by using this formula, which is 1 minus probability of household with a smartphone, which is 0.13. The probability of randomly selecting a household not having a smartphone is 30%. So for another rule, that's a multiplication rule, this is the notation we use. Probability of A and B. Probability of event A occurs in the first trial and event B occurs in the second trial can be calculated by using this formula. And there is another notation. Probability of occurring B slash means given that A has happened already. So the probability of B given that A represents the probability of event B occurring after it is assumed that event A has already occurred. So that's the notation. Whenever you see B slash A, meaning you would like to find out what is the probability of finding B by assuming that A has happened already. So to find the probability that event A occurs in one trial and then event B occurs in another trial, always we need to multiply the probability of event A by the probability of event B, but be sure that the probability of event B is found by assuming that event A has already occurred. So that's the intuitive multiplication rule. So this is the formula we can use when calculating probability of A and B, which can be found by multiplying probability of A times probability of B such that we assume that A has happened already. Independent and multiplication rule. Two events A and B are independent if the occurrence of one does not affect the probability of occurrence of other. For example, let's say we are tossing a coin. First time, it's a head. And now second time when we toss, whatever outcome we got in the first time, it's not going to affect our tossing in second time. That's why the event, for the first time tossing and then second time tossing, we can assume that they are independent event. Okay, so two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of other. Several events are independent if the occurrence of any does not affect the probabilities of occurrence of the others. If A and B are not independent, they are said to be dependent. So let's see one example. 50 test results from subjects who use drugs are given here. So out of 50, 45 of them have a positive test result, and 5 of them have a negative test result. So total number is 50. Okay, now the question is, if 2 of these 50 subjects are randomly selected with a replacement, okay, when you do the replacement, that means now eventually it will be independent events. Find the probability the first selected person had a positive test result and then second selected person had a negative test result. So as you can see here, there are total 50. Out of 50, if you select one of the person, 45 of them could be positive test results. So 45 out of 50, that gives you the positive test result. So if you try to choose 2 of them, not 1, 2 of them, so probability of finding first one positive and second one, find the probability the first selected person had a positive result and the second selected person had a negative result. So probability of finding first person positive and second person negative. Let's say A is a positive and then B is negative. And with the replacement can be found by finding probability of A times probability of B. We can use this formula because we know that A and B are, they are independent in this case because we are replacing the person. Okay, so with replacement, the selection, first selection with 45 positive result among 50 can be found. This is the positive test result, 45 out of 50, and this is negative test result, which is 5 out of 50. If we multiply them, it's going to give us probability of first selection is positive and second selection is negative. And we can multiply this, and these are the mutually, this is the independent events. A and B are independent because we are replacing. But for the part B, assuming that 2 subjects are selected without replacement, when we do that, the second part, we assume that because without replacement they become dependent. Without replacement of the first subject, the calculations are the same as in part A, except that the second probability must be adjusted because it's dependent on the first probability to reflect the fact that the first selection was positive and it is not available for the second selection. After the first positive result is selected, we have 49 test results remaining and 5 of them are negative. So the second probability is therefore 5 out of 49. Remember, in previous case it was 5 out of 50 because we selected, so out of 50, let's say there are 50, where is that, 50 test result from the subject who used the drugs. So out of 50, for the first part we selected first one and we try to find out how many of them have the positive, and this is the answer. And now after selecting that person, again for the second part we are going to replace this person again back in the same group. That's why when you try to choose the second time, the chances of getting the negative from out of 50 is again still 5. But part B, the chances of getting negative, yes, there are 5 negative, but now because we are not replacing, the total number of cases are 49. So that's how we can find the multiplication cases. Either the events are independent or dependent. That depends on that information. Okay. Sampling with replacement, that process is independent events, and if we do sampling without replacement, that's is supposed to be dependent events. And there is a 5% guidelines for cumbersome calculation. Let's say we are dealing with very huge samples, then when sampling without replacement and then sample size is no more than 5% of the size of the population, treat the selection as being independent. Though we are doing it without replacement, but if sampling size is less than 5%, then we can, for the calculation purpose, we can say it's independent. Okay, this is whenever we are dealing with a very huge number. This is the you know the this is the this is the one of the technique we use. uh, you know if our sample size is less than 5%, even it's without replacement, we assume that is independent events. Okay, let's see one example here. In a recent year, there were 130,639,273 full-time employees in the United States. So this is very huge number. If one of those employees is randomly selected and tested for illegal drug use, there is a 0.042 probability that test will yield a positive test result, indicating that the employee is using illegal drug. Based on data from Quest Diagnostics, assume that 3 employees are randomly selected. Remember, 3 out of 130 million, it's a very, very small number. And even you select these 3 employees without replacement, we assume that the chances of getting each of them is same, like this probability. So we would like to find out what is the probability that all 3 of them have a positive test result. So let's say there are 3, first and second and third. Okay, what is the probability of finding all 3 of them positive? Because the sample size is very tiny, we can use this 5% guidelines. We can say that probability of finding first one and second. Okay, so because 3 employees are, we are trying to choose without replacement, so it's assumed to be, dependent, but because of the sample size, 3 is less than 5% of the actual sample, then we can, for the calculation purpose, we can use this 5% guidelines. So because the 3 employees are randomly selected without replacement, the 3 events are dependent, but here we can treat them as being independent by applying 5% guidelines. So because of that fact, whenever we try to find out the probability of first, second and third, we can just multiply the probability of first test positive times probability of second test positive and probability of third test positive, which is 0.042, 0.042, and you just multiply this and it will give you 0.0000741. There is this probability that all 3 selected employee test positive. Okay. Important application of multiplication rule. One thing you have to keep in mind, the principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in an organism can often work in a place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. I'm going to give you one example here. Let's assume that the Seagate hard drive model, this is a model for hard drive, and then failure rate of this model is 2.89%. If your computer has only one Seagate hard drive, what is the probability that will work for a year? So the failing rate is 2.89%. So working rate is, it's a complement of failing, which is 100% minus 289%, which is eventually 97.11. If your computer has 2 Seagate model, then what is the probability of failing? At least one of them will work for a year. So let's look at the calculation here. Where is that? So probability of at least one hard drive does not fail is equal to 1 minus probability of failure. That's because they are complement of each other. So 1 minus probability of failure is 2.89%, which is 0.0289. So we're just subtracting 0.0289 from 1, which gives us 0.971. So that's the probability at least one hard drive does not fail. Now, in second case, case B, at least one hard drive does not fail is equal to 1 minus probability of both hard drive fails. So remember, there are two hard drives in second case, and probability of failing each of them is 0.0289. So it's probability of both hard drive fail is equal to probability of first hard drive fail times probability of second hard drive fail, because they are independent. And we know that the probability of first hard drive fail is 0.0289. Probability of second hard drive fail is again that 0.0289. And if you do this calculation, the probability of at least one hard drive does not fail is 0.999%. 0.999, which is 99.9%. Okay? So what is the interpretation? Interpretation is, if you just use one hard drive, the probability of not failing for that computer is 0.971. But if you use two hard drive, the probability of not failing that computer is 0.999. Okay, that's a huge improvement by a factor of 1 over 28.9. So by using two independent hard drives, the risk of serious failure is dramatically decreased and reliability of the computer is dramatically increased. Redundancy at work. Okay, so these are the summary. Addition rule, probability of A or B. The word or suggests addition, and adding PA and PB, when we must add in such a way that every outcome is counted only once. And multiplication rule, which is probability of A and B, the word and for two trials suggests multiplication, and when multiplying PA and PB, we must be sure that probability of event B takes into account the previous occurrence of event A. Let's look at some example from this section now. Okay, when randomly selecting an adult, A denotes the event of selecting someone with blue eyes. What do P of A and P of A complement represent? P of A represent probability of selecting an adult who does have blue eyes. So probability of selecting an adult with the blue eyes. That's a P of A. P of A bar means complement of P of A, which is probability of selecting an adult who does not have blue eyes. Okay. Let's go to another example. Use the data in the following table, which list drive-through order accuracy at popular fast food chains. So there are 4 fast food chain we are including here: A, B, C, and D. Assume that order are randomly selected from those included in the table. If one order is selected, find the probability of getting food that is not from restaurant A. So to find out how many orders are there, you have to add them all to find out the total number. And you need to find out how many orders are from restaurant A. And from there you can answer this question. I'm going to, because it's available here, I'm going to copy this in Excel to do the calculation, or I can also use my calculator as well. So there are restaurant A, B, C, and D. First of all, find out a total order from each of these restaurants. You can use your calculator or you can use Excel. I'm using Excel and adding this here. So there are 356 order from restaurant A, and if I just select it like this, there are 329 order from restaurant B, 275 from C, 144 from D, and I'm going to find out total by adding all these totals from here to here. So total number of order is 1104. So the probability of getting food that is not from restaurant A is, so we know that there are 356 orders from restaurant A. So out of 1104, 356 are from restaurant A. So what is the number from other restaurants? So if I subtract 356 from 1104, I get 348. So if you select, the one order randomly, there are 748 possibility, which is not from restaurant A. So the probability is 348 divided by the total order, which is, I'm going to, I can use a calculator here, or I can just use 748 divided by 1104. So 748 order out of 1104 are not from restaurant A. So the probability is, if you round it to the 3 decimal place, it's a 0.678. So it's 0.678. Okay. Let's go to next problem. Maybe this one. Okay. Use the data in the following table, which lists survey results from high school drivers at least 16 years of age. Assume that subjects are randomly selected from those included in the table. So if, look at here, this is the table. Drove when drinking alcohol, yes, 729, 181. So these are the total cases who drove when drinking. And out of this, yes, who texted while driving are 729, and no texting while driving are 181. So these are the total number of cases. You can add them all for finding the total case with the, driving after, drinking, driving, no driving after drinking. Okay. What we're trying to find here, the probability that one randomly selected high school driver texted while driving and then drove when drinking. So there are two cases, texted and drove when drinking. So let's find out this thing here. I'm going to I'm going to use Excel one more time. So how many texted while driving? 729. So what is the probability we're trying to find here? So we're trying to answer this question. Find out the probability one randomly selected high school driver texted while driving and when drinking. So we want to find out what is the probability of A and B. In this case, A is it's texted while driving. Texted while, the probability that one randomly selected high school driver texted while driving, and the B is drove while drinking, drove while drinking. Okay, drove while drinking. So we need to find out how many, we can answer this question by if we select one person from this group. You can see that texted while driving 729, drove while drinking. So both of the requirement will be fulfilled if you just focus on this 729 number. So there are 729 the students, they they drove after drinking alcohol and then texted while driving. Okay, so you can answer this question by finding so how many students are there? 729. Out of how many? You have to add all these numbers for finding the total number. So which is 729 plus 181 plus 3209 plus 4530. These are the total students. 8649. Out of 8649, 729 drove after drinking alcohol and then texted while driving. So if you divide this by 8649, that gives us the answer, which is 0.084, and round to the 3 decimal place, so which is 0.084. 0.084. Okay. Okay, we can also answer this question by using this formula, probability of A and B, and these are the two independent events we can assume. We can also calculate this by multiplying probability of A times probability of B, where A is texted while driving. If you can see here, the first column, it says yes. So out of 729 plus 181, if you add this, you are going to get 910. Out of 910 who said yes, I drove when drinking alcohol, out of 910, 729 said yes, I texted while driving after drinking. So that's the probability of A times what is the probability of B, which is drove while drink. So it's 910 out of 8,649 drove while drinking. So there are 910 students from the first column who drove after drinking, and then altogether there are 8,649 students. Out of 8,649 students, 910 they said yes, we did drive after drinking. So this is the probability for B. So if you do this calculation, you can cancel this 10, 9, 10 and 9, 10, and then eventually this gives you the same answer. Okay, let's go to next problem. Okay, among 6,062 cases of hot pacemaker malfunction, 260 were found to be caused by firmware. A firearm or firmware. Yes, okay. Among 6,062 cases of hot pacemaker malfunction, 260 were found to be caused by firmware, which is software programmed into device. If the firmware is tested in 3 different pacemakers randomly selected from this batch of 6,062, and then entire batch is accepted if there are no failures, what is the probability that the firmware in entire batch will be accepted? Is this process likely to result in the entire batch being accepted? Okay, among 6,062 cases hot pacemaker malfunction, 260 were found to be caused by firmware. So what is 260 out of 6,062? It's a less than 5%. It's a 0.042. That means it's a less than 5%. So among 6,062 cases, 260 were found to be caused by firmware. Which software programming? Okay, so in the firmware is tested 3 different pacemaker randomly selected from this batch 6,062, and then entire batch is accepted if there are no failure. So this is the probability of finding the firmware if you select one pacemaker. So because it's 260 divided by 6,062. Now for the 3 pacemaker, as you can see that 3 is the sample size, which is very tiny compared to the the 3 is a less than 5% of total sample size. So for each of these 3, we can assume that the same probability of probability for each of them. So for finding the probability all 3 of them, if they selected randomly, we can assume that the probability of all 3 different pacemaker randomly selected. So what is the failure probability? To find that failure probability, so we can just use this formula. Okay, so there are three. So probability of first one and second one and third one. So there is an AND. Okay, this is AND. We can find the probability of the first one times the probability of the second one times the probability of the third one. We can assume that all of them are independent, okay, because the sample size is very small. The 3 is very small than the sample size. Very small means less than 5%. So what is the first one? The probability is 0.042, this number. And same goes to second one and same goes to third one. So we are multiplying the same thing 3 times. So actually we are just multiplying the same thing. Same thing means this one 3 times. So which is actually the power 3. So this is eventually our answer. As you can see here, it's e to the power negative 0.05. So that's actually 0.40788899. So the probability is, if you round it to the 3 decimal place, it's a point 0.000, which is 7. If you round it to 3 decimal place, it's a 0. This process is unlikely to result in entire batch being accepted. No, this process is likely because finding the firmware is very low here. Okay, what did I do wrong here? The probability is okay. So what I did here is I found the probability of failure, but actually we need to find out the probability of what is the probability that the form in the entire batch will accept it. So we need to find out probability of acceptance, not the failure, which is a complement of this number, which is actually, if we go back and try to find out what is the probability of failure, which is 260 divided by 6062, and we need to find the complement of this, which is 1 minus this number, 1 minus this number, which is 0.957109, and this is true for this should be the number I have to use here instead of 0.042 3 times. So the multiplication of this thing 3 times, which is the answer to the power 3. So this is the answer, 0.8767, which is 0.877. So the probability is 0.877 of acceptance. The process is likely. So let me just go back and check it again. So instead of multiplying by probability of success, I multiplied by probability of failure. That's why my answer was off here. So you need to find out the probability of success by finding the complement of the probability of failure. So I forgot to subtract answer from 1 for finding the probability of success. Okay, let's see next one. Complete the following statement. Probability of A or B indicates it's the probability that event A or event B does not occur in a single trial. The probability that A and B both occur in a single trial. The probability that in a single trial event A occurs, event B occurs, or they both occur. The probability that event A occurs in one trial followed by, okay, this one is the answer. The probability that in a single trial event A occurs, event B occurs, or they both occur. That's the meaning of probability of A or B. Okay, let's see one more. Fill in the blanks. 2 events A and B are if the occurrence of one does not affect the probability of the occurrence of other. They are mutually exclusive, disjoint, independent. 2 events A and B are independent if the occurrence of one does not affect the probability of the occurrence of other. Excellent.